the chair for the session. I am Nicholas Brunelli. I'm at Ohio State University. I'm an assistant professor, and this is my co-chair. This is Amarish Murkute. He's at Babcock and Wilcox, and we will be chairing today. I'm very pleased to introduce our first keynote speaker, Israel Wachs. Ultimately, he's going to produce some very interesting spectroscopy, which he always does, and provides unique insights that allows him to design unique style of catalysts. So with that, I'll let you go ahead and get started.
Thank you. Need the pointer here. Okay, let's see it. Well, I want to thank the organizers for selecting me to do the keynote presentations. I'm really honored. And I also want to thank my collaborators who I'll be mentioning throughout this presentation. This work would not be possible. So the person who did the work was So Lewin. He's my graduate student. He just graduated. He's wrapping things up right now. Anybody's interested in hiring a newly minted grad student, he's looking around for a job. Also, Chris Keterakis, also another grad student who has graduated. And I've collaborated with Professor Hanslick in Poland and Philippe Sauté in France, who did some DFT that I'll briefly show. Also we did some X-rays, X-ray absorption spectroscopy in Brookhaven National Laboratory with Anatoly Frankel and of Yeshiva University and Brookhaven National Laboratory, and also Albert Steinman at Florida State University, where we did some high field EPR, which I'll share with you. I won't necessarily show all the work, but I'll refer to it. Why this topic? Shown here on the left, oops, sorry about that. Shown here on the left is production of propylene. And this is produced by flute cracking, and this is produced by steam cracking of propane. Okay? And this curve up here is the demand. And so you have a gap, and there has been a gap, and it will continue for quite some time until we have new capacity in plants to meet this gap. And so here you can see is how much is missing, and this is the technologies being developed, new technologies, to make up for this shortage in the world of propylene. It's expected to continue to about 2025 currently. And you see that most of this technology here new plants are being built for propane dehydrogenation. And that's this blue, and this sort of bronze, orangey colored is metathesis. And you can see that the metathesis technology, there are dozens of plants being built around the world to meet this shortage. And although the Nobel Prize 10 years ago was given for olefin metathesis, it was for homogeneous olefin metathesis. Okay? And these plants here are large volume, not specialty chemicals, and they're using the supportive metal oxides, heterogeneous catalysts. And this, of course, is the reaction that we're going to be looking at, reacting a molecule, an olefin, and what happens is you transpose both halves of the molecules. In the case of, if you want to make propylene, you run ethylene and butene, 2-butene, to do this. And these are the different transitional metal oxides that can do metathesis. And so far, so far of the heterogeneous, which I'm going to focus on, the supports have been silicon and alumina, and the metal oxides have been tungsten oxides, rubidium oxide, and rhenium oxides. Those are used for high volume, small olefins, non-specialty chemicals which tend to be more homogeneous. And today I will focus on the rhenium oxide catalyst. It's actually one of the most studied, but even though it's the most studied, still, as you see from the literature review, there's still a lot of confusion about this. The molecular structures of the metal oxides that are supported are poorly understood, how they interact with the oxides, the oxidation states of the metal oxides during the reaction. And a big debate in this area is the number of participating metal oxide sites, catalytic active sites. Some people claim that it's on the order of 1%. Others are saying that's 13%. And I'll show you how this measurement is done and comment about this. There's also the initiation mechanism is somewhat unclear. The surface reaction intermediates, and some people report first-order kinetics, and some people report second-order kinetics. So there's also a conflict in this area. There's a lot of work. This metathesis, open metathesis, was discovered 51 years ago, and so of course in subsequent years in the 70s and 80s, this topic received a lot of attention. But there was almost no in situ studies, and certainly there were no operandum spectroscopy studies during this period. And so for about 20 some years now, 25 years, this area has been pretty quiet. But now, because of the demand, it's taking a lot of interest in this topic. And so there has been no in situ and operandum spectroscopy studies. And what we want to do is approach it from what's called a modern approach, to actually use in situ techniques during the reaction, and to see what is going on and what is the relationship between the structures we see and the performance of the metathesis. Then we want to use this, of course, to design an improved catalyst, to rationally design. So the approach we're going to take is we're going to do in situ and operandum spectroscopy to get at the molecular electronic structures and the kinetics of this reaction. And here are listed the different techniques that we use. The UVVIS, ultraviolet visible spectroscopy, tells us the oxidation states of the rhenium oxide, and also the extent of oligomerization. For example, is it a monomer, a dimer, polymer, or cluster? There's been multiple claims in the literature about the structure. Raman will give us molecular structural information for the rhenium oxides from its vibrations. IR can look at reaction intermediates and surface aluminum hydroxyls to tell us where the rhenium oxide is anchoring to. I won't show you the IR because it's very, very complicated and very difficult to actually break down. All we see is a lot of high bonded propylene on the surface. We tried to do carbon 13 NMR with Christophe Coporet. However, you have a small amount of paramagnetic rhenium under reaction conditions, and it interfered and broadened the signals, and so that didn't resolve it, but we're still going to try to get at this. But anyway, I just want to mention that. We also did in situ X-ray absorption spectroscopy to get at the local structure. Again, the coordinations and so on of the rhenium oxide. I won't show this as well because of time limitations. And we also, in collaboration with Professor Hanslick in Poland and Sauté in France, we looked at some DFT calculations to see what we could learn from there. And then to get at the reaction, we did two kinds of kinetic experiments. One was steady state reactions, and we also did temperature programmed surface reaction spectroscopy to get transient information about the kinetics. And we also used isotopes, deuterated molecules. So, to make the catalyst, it's pretty straightforward. It's probably the easiest catalyst to make. It's just pyrenic acid, and you impregnate it, base it, and you wet this into the alumina, and you dry it and calcine it, and then you get the rhenium oxide. So the rhenium is +7 when it starts out, and when it's oxidized on the surface, it's still +7. And you get the rhenium content from ICP analysis and also from quantitative hydrogen temperature program reduction. And the reason is, I won't give the answer away, but you'll see why we also did a hydrogen TPR in a while. So the first question is, there's debate in the literature, what is the state of this initial rhenium oxide here? And so here you have, in order to answer this question, there's multiple techniques to answer this question, but the best is actually ultraviolet visible, because we're looking at the optical band gap, and this optical edge energy goes down as the metal oxides oligomerize. And so what I have here is two reference compounds. This is an oligomer of solid Re2O7. And here I have several reference compounds. And so the oligomer has an edge energy of 2.9, and the monomers of rhenium oxide have 4.0 electron volts. And these are different catalysts that we made, and you can see that they're all in this region of isolated. And indeed, if we do XFs, we do not see rhenium, oxygen, rhenium being present. And also in Raman, you can see the bridging band, rhenium, oxygen, rhenium, and it's absent. So all techniques tell us that indeed we are dealing with isolated. So it's truly an isolated site catalyst. The rhenium oxide is also volatile, and one of the reasons why you don't make oligomers is that once you make oligomers, they're volatile. And so it's a self-correcting system that if you put too much, and when you calcine, it'll make Re2O7, which is a gas phase molecule, and just leave the surface. That's why you have to quantify how much rhenium is in the catalyst. So shown here is the Raman spectrum of low-loaded, actually it's 3% rhenium oxide on aluminum. And I've only shown just the Raman intensity, this is the vibration, and this is the rhenium oxide, and this is a double bond, and it's at 1,002 wave numbers, and this is symmetric stretch, this is the asymmetric stretch. If we go to a higher loading, the Raman spectrum shows a second peak now, and we have a second species. So even though this catalyst consists of isolated sites, there are two isolated sites. Okay, and so this raises the question, of course, what are these structures, where are they, and what role do they play in the catalysis of this reaction? And as you can see, it added to the confusion in the literature because people were not aware that there were two sites. They were treating them as one collective site. So here is, I'm turning out to infrared. I want to see where the arena is sitting. And Philip Sauté and co-workers have done a very, very nice, really beautiful work on identifying the different hydroxyls that are present on alumina. So the first thing you can see there are 5 different hydroxyls where you have the hydroxyl bonded to one alumina called mu1, bonded to 2 alumina called mu2, and then even 3 aluminas over there. So you have different alumina sites. And so right away you see that the surface is heterogeneous. And here on the top is the IR vibrations of the hydroxyl regions, and you can see multiple bands. And as you start putting rhenium at low loadings, you see that this band here, the so-called mu1 bands, are disappearing first, labeled in blue. And at higher loadings, also these other bands, hydroxyls, are being consumed. The rhenium is sitting on there. And it's also known in catalysis that these tend to be a bit more basic, and these over here tend to be more acidic. And so, again, it's no surprise that we have 2 sites for rhenium oxide because the surface is truly heterogeneous. And that's why we call it heterogeneous catalysis. So we turned this problem around and we said, okay, since the first rhenium oxide seems to be sitting on the basic sites, what if we put another oxide on there that's sort of acidic, and can we, in a sense, titrate these basic sites, and therefore we'd only get the second species. And so we did this preparation, and where we first put tantalum oxide and calcined it, and then in the second step we added the rhenium oxide. And here is again the IR spectra of alumina, and you can see that putting tantalum indeed removes selectively, preferentially initially, these hydroxyls here. And when you add the rhenium, you get more reduction of some of the others, hydroxyls as well as some of this as well. But let's look at the infrared, the Raman, to see what rhenium we have. And what you see here is that the band for all of these catalysts is only a 1010. That's the second species. Okay, and the reason we picked tantalum oxide is because we knew the Raman spectrum was very, very weak. Although it's in the same region, this is the tantalum oxide on alumina, and this is 1% rhenium on alumina, so you get very nice rhenium oxide vibrations and not really being affected too much by this. And you can see that at all loadings, as long as we have tantalum oxide, even for 1% rhenium oxide, we don't have the band at 1,000, we have it at around 1010. Our resolution is better than one wave number in our instrument. So about 10 wave number shift is very significant. And these bands are indeed quite sharp. So with using tantalum as a promoter to block the formation of the ReOx1, we can make catalysts that have exclusively ReOx2. Now the question is, what is the structure of these rhenium oxides? And in the literature, you can find many structures being proposed, and this is I would say, a most favorite structure. Dioxo has appeared in recent years by some papers. The DFT calculations done in Europe have shown that this ReO5 dioxo is not stable. And we looked at the stability, and actually this wasn't stable and this wasn't stable as well. But I'll show you experimentally what we did to nail this structure. So what we did was we turned to oxygen isotopes. And it turns out that because oxygen 18 is heavier than oxygen 16, you have a shift, quite a significant shift in the Raman vibrations of the rhenium-oxygen bonds. And you can use this to discriminate between trioxo, because trioxo, when you scramble the oxygens, you have 4 permutations, you get 4 bonds. Okay, you split this vibration into 4, and in the case of dioxo, you split it into there's 3 permutations, so you get a triplet, and in the monooxide you get only 2 possibilities. And so this is what we did. And on the left is shown the results for oxygen scrambling. And this is time resolved in situ, where we're adding oxygen 18 and using H218O to replace this. And here's the original. So this is the ReOx1. This is the original vibration. And as you start scrambling and adding oxygen 18, you see that this peak at 1,000 is moving over in the intermediate range where you have the scramble with oxygen. You have 992. And finally, when you complete the exchange and this band at 1,000 goes away, you have this other band at 943. So we see only 3 distinct bands, which is consistent with a dioxo structure. And this is for the high load of the second species. We do the same experiment. This band is at 1010. And again, when you start adding the oxygen, it moves to this band, 995. And finally, when you complete the exchange, it's at 950. And so again, we see only 3 bands. Okay, so this is consistent experimentally. And so what I did next is I contacted my colleagues who were doing the DFT. I didn't tell them my results, and I asked them to please go back to their calculations and start scrambling the oxygen with oxygen 18 and see what they get. And here is the results for the first one. And so these are the DFT calculations, and here is the experimental results. And you can see that when it started scrambling, we get very similar for, this is with 1 oxygen 18, this is with 2 oxygen 18s in these vibrations here. So we have very, very good agreement. That's for the low loaded, so-called ReOx1. And here's the calculations for the high load of the second species, when we use tantalum oxide to make the catalyst with only 1 site, only the second species. And so indeed, we have dioxo species, and it's ReO4, as also shown by Xames in the Raman selection group. Okay. So now we know the structures. Now the next question is, so now that we know what the structures are, what do they do? What do these 2 sites do during when you expose them to propylene? So this is an operando spectroscopy study where we are simultaneously monitoring the catalyst with Raman and monitoring the products online with a mass spec. And what you see here, so I picked this catalyst because it has the two species. The first one and the second one are. And you can see that we introduced propylene. This reaction is reversible. You can go back and forth. And at various times in this talk, I will occasionally do that. And you can see that you're making ethylene and 2-butene as a reaction product. So the reaction really is, we know that it's occurring, and we actually can measure the reaction rates with that information. But if you see here, we allowed the reaction to run for almost 2 hours. We collected the spectra all along, but it was too crowded on the slide to show you, so I just showed you the starting point. And the surprising part is that only the vibration of the second species disappears. The first one is unperturbed. Okay? That's very, very interesting. So the two species are not behaving the same. Okay? They're not responding the same way when exposed to propylene. But to get more information, we turn back to ultraviolet visible spectroscopy. And on the left, I have reference compounds for rhenium +7, +6, +5, +4. And here I show the different spectra. And what you see here, if you run it at lower temperatures, like 70 degrees C, is a little bit of these bands, which are +5. If you raise the temperature to 150, you do the reaction at 150, it's still taking place, but the surface coverage now is very low. And now you see a lot of +5 on the surface. And so the apparently happens, so an oxygen is removed from the rhenium, and the olefins are coordinating to the rhenium, and therefore inserting its electrons in the double bond and to reoxidize the rhenium +5 back to +7. There's also a trace of +6, so there's been UVVIS, and that's why we went down to the magnetic center down in Florida, the National High Frequency Magnetic Center, the UVPR. This is Albert Steigman, collaborated with us, and unfortunately you can only see +6 in EPR, only the paramagnetic species, but rhenium +4 is also paramagnetic. There's no rhenium 4, so it cannot detect rhenium +5, but it does confirm the +6. But the UVVIS is clearly consistent with the +5 rhenium being there. So it's basically like a redox cycle. That when it has the propylene bonded, coordinated, the rhenium goes to +7. When the olefin leaves, it goes to +5, and then we accept again another olefin. Okay. So now the steady state kinetics. So I plot here the activity in the units of millimoles of product per gram per hour as a function of the rhenium content. And remember that we had the first rhenium at this low loading here. Actually, I could quantify, and that's why I mentioned earlier about the hydrogen TPR. You can actually get two, they don't reduce identically. And you can see that the second rhenium reduces very easily, and the first rhenium it reduces at a higher temperature. And this allows us to quantify how much is the rhenium +1, the ReO41, and it turns out to be 3.2%. And the rest is the ReO2. And notice right away that the first species, which didn't respond in the Raman when we introduced propylene, is not reacting. Okay. So it's not only is it not reacting, it's not even bonding with the propylene, because that would perturb the vibrations of rhenium. And once you start having the second species, the reaction takes off. And the more rhenium you have, the more you have of the second species, and the reaction takes off. So then we used our catalyst where we block formation of the first species. Okay. So remember, so this was a case where we used an acidic promoter to block, to titrate the basic hydroxyls and not allow formation of the ReOX1. And right away you see there's an increase in activity, and you can see that all at the same loadings we have a much more active catalyst. Okay, because now we have this catalyst has no ReO41. It has only 100% ReO42, which is the active site. If we move this over to compensate for the fact that we block the ReO41, notice that these two curves overlay totally, and you can see that it's stopping, here at, it's stopping, at this point here where you have, we prevented the formation in this region of the ReO41, which is about 3.2%. So we were intrigued by this observation, and we looked at other promoters, and we also, the reason we used tantalum oxide, it was just because for the Raman purpose, because it didn't have a Raman signal, and made life very simple for us to look at the rhenium oxide vibrations. But here we use silica, and here we use the tin oxide, which is added to these catalysts, but added as an organometallic compound. This is an oxide. It's not the same. But nevertheless, what I want to show you here, here's the low-loaded 3% rhenium oxide alumina, and here you only have the first species, ReO41, 1001. Notice that as soon as you add any of these other promoters, and they're occupying the basic hydroxyls, that the band shifts to 1011. Okay? So let's now look what happens. So these catalysts have only, these promoter catalysts have only ReOx2, ReO42. And here I've plotted the activity still in millimoles per gram per hour as a function of loading. So here's alumina, and you have like 100-fold increase in activity per gram with all of these promoters. The tantalum turns out to be the best silica intermediate, and the tin a little bit less. But all of these have a very, very profound effect, and 2 orders of magnitude increase in activity in olefin metathesis. This is for propylene, and this is done at 70 degrees C. So a big question in the literature, as I mentioned in the introduction, is people are debating, very voraciously debating this issue, how many sites of rhenium are actually doing catalysis. Let me take a break, get some water here for a second. And so the way they do it is they will absorb either propylene or 2-butene on the surface, and which is proposed to create these intermediates, and then they will evacuate for 4 hours, 4 to 6 hours. Okay? Full vacuum on the catalyst. And then they come back and they will titrate these intermediates with either undeuteраted ethylene or deuterated ethylene. So if you titrate this guy here, you add a CH2 and you make propylene, and if you titrate this ethylene with this CH2 intermediate, this carbene, you'll make ethylene. And so in order to discriminate between the ethylene reactant and the ethylene product, they then also use deuterated ethylene. So then they'll get a mixed product. But I was very concerned, that you go back and do a titration after pulling vacuum for several hours. And so I have some problem with this, and we want to reproduce this. And also the issues like partial pressure effects, temperature effects, and promoters are debated, but I won't discuss this because of the limited time. If somebody has a question at the end, I'd be happy to discuss it. Okay, so on the left side, what we do is we're monitoring in real time. We absorb 2-butene, and then we're flowing ethylene. Okay, so we saturate the surface with this intermediate, and supposed to be making the C2 carbenes, and then we come in with this, and this will make 2 propylenes. Okay, and what you see here is a function of time as we introduce the ethylene flow, and you can see that if you switch right away when you saturate the surface to the ethylene, you get a big amount of propylene being formed. But if you wait 30 minutes, 60 minutes, 4 hours, you can see that you're losing the intermediates. And you can also see this in infrared. Okay? So this reaction is reversible. So if you pull vacuum, and you don't have this in the gas phase, you have ethylene, but you don't have the butene, this reaction goes back. and then it's flushed out. So you're making. I don't show here. We also see propylene. This is the propylene. But we also get some butene, but I want to say, coming off here as well when we introduced the ethylene. And we integrated these curves. So first of all, this assumption that the intermediates are frozen for 4 hours in vacuum is an incorrect, and it's basically undercounting the number of sites. And using this very quick switch, we can actually quantify how many intermediates we get. And here, the black curve shows that the number of surface intermediates goes up to about 5% or so. And this is where we have the first species, REO 41, and here where we have the second species also, and it's reasonably leveling out here. And so you can see here, I've taken the ratio of how many propylene molecules we formed and dividing by the rhenium, and you can see that when you have the REO42, the second species, you can get about 8%. If we add tantalum, where we got rid of the REO41, we actually get 10%. Okay, because now all the sites are absorbing. Okay, so we're an order of magnitude greater than the claimed 1%. Okay, but this is still not the end of the story. So by titrating immediately, you get 10 times more intermediates. You don't get sites, you get intermediates, and that's been a misconception in the literature. We have now also, spectroscopy, and we can monitor the intermediates. Intermediates as well, but we can monitor the rhenium. And so here's the catalyst where I use tantalum, and I block the formation of the first one. I only have the second species, which is at 1010. And notice that this band is going away completely. Okay? And so every single REO42 is bonding, exposed and bonding to the olefin, to propylene in this case. And since rhenium is volatile, we reoxidize just to make sure that the signal didn't decrease because we lost rhenium to the volatility. And when you do this, you see that indeed it comes back. And so the answer is titration is just a titration, and there are all kinds of steric hindrances going on the surface. Okay, and even though you're getting a 1 to 10 ratio, all the REO42 are exposed, as shown by this Raman, and all are participating. And so it's the REO41 that's dead, but the REO42 is participating. And now, knowing the number of sites, we can calculate the turnover frequency. Until now, I was giving you the values just in activity per gram. And so here is the unpromoted catalyst, and this is for the first one, the REO41. And you can see, it might need a trace of the active REO42 there, I don't know, below my detection limits, but it has a very, very low activity. And you can see I jump almost 100-fold when I have the tantalum blocking the first site. And these catalysts here were subtracted by 3.2, the rhenium content was subtracted by 3.2% RE41 because that has a very, very low activity. And we wanted just to calculate for the active species. And you can see you get this relationship. And this now is the turnover frequency for the pure, 100% pure active sites. So we've made 100% pure active sites. And you see here it's about 10 to the minus 3. And at higher coverage, it's about 10 to the minus 2. So what's interesting about this, somebody who's been playing around with this stuff for decades, is that this is not flat. The TOF, the turnover frequency, is actually going up. It means there's steric hindrances or something more is going on. And when we plot this at a log, are involved in the reaction. It's always been assumed that only one site does the reaction. Okay. This gets back to this controversy: is a first order or second order? And if you run the reaction at low temperature, modest temperatures, you get first order kinetics, first order propylene. However, if you raise the temperature, you get almost second order kinetics. So there are two mechanisms operating. I have to point out, most of the work has been done at low temperature, but there are people who've claimed second order, and if you look at their papers, they're operating at elevated temperatures, like 100 C or thereabouts. So that explains that. So to learn more about this reaction, we absorbed undeuteurated propylene and then titrated that with deuterated propylene, and then ramped the temperature. And you can see here, for example, the mixed isotopes. And so you can see that the CD2 fragments from ethylene reacted with the C2 fragments and the C2 carbene as well, fragment. But what surprised me about this is that the peak temperature is the same for all of these. There's a common intermediate involved in all of this. Furthermore, well, I'm not showing you here, if you vary the coverage of these molecules, this peak temperature goes lower and lower. And for those of you that are familiar with temperature probing technique, that's characteristic of second order. So this high temperature olefin metathesis is a second order reaction. So to conclude, I have a question to the chairman. My clock says 4.5 minutes. Is that the total time?
Yeah, there's about 4.5 minutes.
Out of 30 minutes, so 25 minutes.
That's a 5-minute one.
It's a 40-minute talk, and you have about 4.5 minutes or 5 minutes for questions. Yeah.
Okay,
Currently.
5 minutes left. Okay,
Correct.
Thank you. So good timing. It's going a little fast to make sure I can cover all this. Okay, so what do we discover? We discover that we have this species. They're dioxo, and there are two species. There's the first one, I label as 1, and this one is very inactive, very difficult to reduce, and it has a turnover frequency of 10 to minus 5, and even this minimal amount of activity may be from a trace of the active species. They're rooted into that. We don't know that. It's below our detection limits. The active species is the second species, and it has a turnover frequency that's coverage dependent between 10 to minus 3 and 10 to minus 2. So it's going up. And all the surface ReO42 sites are active. Okay? And if you look at a lot of the publications, they usually study lower loadings of rhenium oxide. And so they had mostly, another reason why they were getting low numbers for active intermediates, they were looking at catalysts that were basically dominated by inactive rhenium 0401. This knowledge that there were two species there and the ability to block the very low activity or essentially inactive rhenium oxide allow us to design catalysts with 100% ReO42 that were very, very active. As you can see here, 1 to 2 orders of magnitude more active. The olefin metathesis reaction kinetics is temperature dependent. Okay. It's first order kinetics at low temperatures, presumably going through a metallocyclobutane decomposition. At high temperatures, meaning like 100 degrees, 150 degrees range, it's second order, it's a bimolecular reaction. Two intermediates are reacting. The CH bond breaking is not involved in this reaction, as shown by the lack of kinetic isotope effect. And I'd like to thank the Department of Energy, Basic Energy Sciences for supporting this work. We're extremely grateful. The collaborators in Europe doing the DFT calculations, the operando X-ray absorption spectroscopy did not show with Anatoly Frankel and his postdoc Aaron Kovic, and Albert Steigman. Also, I didn't show you the EPR to see what more we could learn with the high field EPR. So thank you for your attention. I'd be happy to answer your questions.
Do you have any questions?
My name is Jimmy Liu from the University of Oklahoma. You use Raman to check the rhenium species before reaction, and also you found the rhenium species can be reduced by the hydrocarbon, especially you run the reaction in a reductive environment. So did you check the rhenium species after the reaction, and what is the active species? In your conclusion, you said it seems you think rhenium-7 is a really active species?
Well, here you can see that even though it's a reducing environment, only the second species is reducing, not the first. And from XFs, hexanes in particularly, and the UVVIS, we see rhenium +5 being a dominant reduced species. I do not know at this point what that structure is, okay? But it's +5, so I can tell you. We'd have to do theoretical calculations to try to assign this +5.
So because rhenium species may be reduced during the reaction, will that cause a deactivation?
No, because it goes back and forth. I told you there's absolutely no +4, because you can see the +4 is paramagnetic, and you do not see it in high field EPR. So there's no, it's only rhenium-7 and rhenium-5 going back and forth. Somehow, maybe there's some side reaction, or you get some cracking or something, and you're a trace of rhenium-6. Those are the only 3 species. But the active cycling is between +7 and +5 rhenium.
What's the difference between the two sites, the dioxide sites you talked about?
They're slightly different. I mean, they're sitting on different sites, and in a sense, the ligands are different. So let me see here. The DFT calculation shows this very nicely. I'm going the wrong way. Okay, sorry about that. No, I'm sorry. It's here. So this is the 2 rhenium sites. They're not identical. And the important thing is they're not sitting on the same alumina sites. And Christophe Copperet has this very fantastic new NMR that's super sensitive, and he's trying to look at these surface alumina sites. And basically, this alumina site is a very reactive site, and therefore holding the oxygen very, very strongly. And even with hydrogen, it's difficult to reduce this first rhenium. And the second one is very easy to reduce. So they're not. They obviously, you can see there's 2 bands. They're close, but they're not identical. And chemically, one's dead, meaning that it cannot be activated, and one can be activated.
I noticed that Harold here. I noticed that the amount of modifiers or promoters that you use, weight percent-wise, is quite different for the 3 different promoters that you use. I assume that you've studied different weight loadings of them, and the data you report are the optimum numbers. So then the question is that in terms of modes, are they very different also? And if they are, do you have any insight in terms of why they promote the blocking of the number 1 site differently for different promoters?
We did not do multiples. We just slapped on these concentrations. And the reason is, all we were trying to do is titrate away these basic hydroxyls. And you can probably, I guess we didn't know a priori how much tantalum would do the job. We wanted to really make sure, so we dumped half a monolayer of tantalum. But once we saw that and realized what was going on from this IR, when we put the tin and oxide in the silica, we cut back because we knew we were over-titrating. There was not that many basic hydroxyls, so you use much lower contents. And this is the reason. All you got to do is make sure that you get rid of these hydroxyls, then you get only ReO4 sites on this catalyst. The loading is not, there's a minimum like 3%, okay, something like that, to titrate the basic hydroxyls. Beyond that, it's just extra. It's not helping.
Thank you, Israel, very much. Great talk. Ultimately, it's very interesting how you can reconcile a lot of this metastasis data. Thank you very much. I thank the speaker once again.